Hello again. Today we're going to be talking about functions that are defined by integrals. So let's get started. Sometimes a function isn't expressed explicitly as a polynomial or some other kind of function. It's expressed as the integral of another function, which is called little f of x. And sometimes we may not even be given what that function f of x is. We may be given f of x in the form of a graph. And we still need to be able to answer questions about the integral function that little f of x is inside of. So let's look at an example. This is the graph of little f of x equals 2. And I need to know some things about capital F of x. Capital F of x is defined as the area under that curve from 1 to some other unspecified number that I plug in as an x. So if I plug in different numbers, let's see what happens. If I plug in x equals 3, then I'm finding the area under the curve from 1 to 3, and that gives me an area of 4. If I plug in x equals 2, I'm finding the area under the graph from 1 to 2, and that gives me an area of 2. If I plug in x equals 1, that means I'm finding the area under the curve from 1 to 1, and that actually covers no area at all, so the area would be 0, and that makes sense. Now if I plug in a number that is less than 1, like 0, now I'm actually going backwards from 1 to 0, and that means that even though the area is above the x-axis, I'm going to the left, so I have to consider that to be a negative area of negative 2. All right, if I did more of those, then I could create this table, and I would see what I notice from those x values and those y values. And what I notice is that that table actually represents the function of y equals 2x minus 2. So I can also represent the capital F function as capital F of x equals 2x minus 2. That makes sense because the derivative of that would be 2. And since little f of x does represent the derivative of capital F of x, then all of those properties that we've talked about before still hold. So capital F of x is always increasing. The y values are going up. And f of x is always positive. It's always positive 2. Capital F of x has no maximum or minimum. It just keeps going up and up and up. And little f of x never changes sign. It's always positive 2. Capital F of x has no concavity to it, and little f of x has no intervals of increase or decrease. It just stays the same. So here's another example that might be a little bit more difficult. We've got a line with a slope there, a slope of 2 by the looks of it. And now capital F of x, again, is going to be the area under that curve from 1 to another number x that I'm going to plug in. So I'm going to plug in some x values and see what happens. If I plug in 3, then capital F of 3 is the area under that red line from 1 to 3. And if I add up all that area, that adds up to 8. If I plug in 2, then the area from 1 to 2 is going to be 3. If I plug in 1, then again, the area from 1 to 1 is not going to cover any area at all. So that has an answer of 0. And now, if I'm going backwards from 1 to 0, then I get that red triangle, which has an area of negative 1. It's red because I'm going backwards. And then if I go all the way to negative 1, now I've got that red triangle from before, but now I've got that new area from 0 to negative 1. And I'm going backwards, so that produces a negative. Also, the area is under the x-axis, so that creates another negative. That double negative makes that green area positive. So if I'm looking for the area from 1 to negative 1, I've got the red triangle and the green triangle combined, but since they have the same area, they will cancel each other out, and my total area will be 0. So if I do more of those, then I get another table that looks like this. And here's what I notice about that table. That table actually gives me the equation capital F of x equals x squared minus 1, and you can plug in the x's and see that you get the y values underneath each of them. And that is the actual function. And that makes sense too, because little f of x, which is supposed to be the derivative of capital F of x, is actually 2x, and that is the derivative of x squared minus 1. So all of those properties hold. Capital F of x does show a minimum value in the table at x equals 0. The y value there is negative 1, and none of the other y values are any lower than that, and they never will be. And little f of x in the graph that changes from negative to positive at x equals 0. So there's that relationship between a minimum on a graph and a change in the derivative from negative to positive. Now, capital F of x has no maximum because it is an upward-facing parabola, so it doesn't have a maximum. And that makes sense with the derivative, because if there was a maximum, little f would change from positive to negative somewhere, and that graph doesn't actually do that. Also, capital F of x, because it's a concave up parabola, it's always concave up, and that means that little f of x is always increasing, which it is. All right, now here's a true example of what you would see on a test or a quiz situation. So we've got a graph, and we're not really going to try and find the function this time, but we are going to be able to answer some questions about this function, capital F of x. That is the area from 2 to some other number x. So I need to, first of all, identify all the local maxima and the minima of capital F of x. So what I'm going to do is I remember that if there's a maximum or a minimum on capital F of x, what that means is there's going to be a change of sign in the graph. The derivative is actually going to go from positive to negative or negative to positive. I see that there is a change from positive to negative on the graph at -1, which means that there's going to be a local maximum on capital F of x at the same x value. If there was a change from negative to positive on this graph, then that would be a local minimum, but I don't see that anywhere. So there's only a local maximum on the graph of capital F of x, but there's no local minimum. And some of you might be looking at x equals 4 because it does touch, the graph does touch the x-axis there, but because the graph does not change sign at x equals 4, then I can't say that there's a local maximum or a minimum on capital F of x. All right, let's discuss the concavity of capital F and find all the points of inflection. So if I'm finding points of inflection for capital F of x, what that means is on the graph, which represents the derivative, there's going to be a change of direction. It's going to go from increasing to decreasing or decreasing to increasing. And there's 3 places where that happened, and I've indicated that with those arrows there. Those are the places where it changes direction. Now, when the graph is increasing, what that means is capital F is going to be concave up. And when the graph is decreasing, that means that capital F is going to be concave down. And so when little f is decreasing, that means that capital F is going to be concave down. All right, so I've got my points of inflection there at -2 and 0 and 4. And I notice that because the graph is increasing from -4 to -2 and from 0 to 4, then the function capital F of x is going to be concave up for those x's. And then because the graph is decreasing from -2 to 0 and from 4 to 6, that means that capital F is going to be concave down over the same intervals. All right, now let's talk about a global minimum and a global maximum. Now remember, when we were looking for a global minimum and a global maximum before, I would look at the critical points and the endpoints of my function capital F. So there was a minimum at x equals -1. I found that before, so that's going to be considered a critical point, and I'm going to consider that. And then my endpoints are -4 and 6, so I'm going to consider those as well. If I plug in -4, then what I've got is I've got this green area, which is below the x-axis from 2 to -4, and that's backwards. So the green area is because I'm going to the left, and the area is below the x-axis. So that's another double negative, so that makes it positive. And then the area from -1 to -4 is above the x-axis, but because I'm going backwards, it is a negative area. So the green area has a total area of 8, and the red area has an area of -6. So combined, that is a total area of 2. Now if I plug in just -1, then that only takes care of the green area, which, as I said before, was 8. And finally, if I figure out the area from 2 to 6, all of that is below the x-axis. There's 2 triangles there that I have to consider there. They're both under the x-axis. They each have an area of 2, so the total area there is -4. So looking at those 3 y values, the highest of those is 8 and the lowest of those is -4. So I can say that the global minimum is -4 and the global maximum is +8. So that's how I would find out information from a function that is defined by an integral. If you have any questions, please let me know, and I will see you tomorrow.